Very good afternoon to everyone, and it's nice to know the excellent work being carried out by ICCW. And I would like to thank Professor Pradeep for giving me this opportunity to interact with you all. Hope I am audible and the screen is visible.
It is visible, but not full screen though.
Yeah. Is it fine now?
Yes, very good.
Yes.
So can I proceed?
Absolutely, absolutely.
Yeah, very good afternoon. And the topic of today's discussion is going to be like how remote sensing or observations from space can really help to monitor water resources and to assess its quality. And we all know that the work that is being done by the ICCW with regard to assessing the water quality. But when you want to monitor a larger area, for example, hundreds of lakes, rivers, estuaries, and oceans, etc., then probably space technology is one solution where you not only do the water quality assessment at local level, but you can also do it at global level. And if the participants are having preliminary knowledge in remote sensing, probably the first few slides may be redundant to them, but nevertheless, I thought it may be necessary to give a brief overview of what this technology is. And we all know that remote sensing, by definition, is nothing but trying to know something about an object without being physically in touch with it. So I don't touch the object, but observe from a distance and try to observe certain characteristics of the objects. And then based on that, try to find out what object that is, where that object is, what is the size of that object, and what are the qualities, and so on. So inherently, without being physically handling the object, you are trying to sense something, which basically we all call as remote sensing. And of course, remote sensing today, you can do it using a drone, but the problem with the drone is that it can give you very good quality of pictures, but it can see only a smaller area, maybe suitable for, say, 5 square kilometers or 10 kilometers in a day. And other possibility is to use aircrafts or helicopters where you are airborne and fly over an area, acquire data, and then analyze the data to produce the deliverables and results. But again, this requires you need to fly every time. You need the data. The third possibility is to use satellites. So you design a satellite and then put it in a rocket, get it launched from the launch pad. The rocket puts the satellite into the orbit. And then once it reaches the orbit, it goes around the Earth almost for the design period. Normally, the design period may be 4 years or 5 years. For the entire 4-year or 5-year period, the satellite is going to revolve around the Earth and continuously sending the data to you so that you can monitor whatever you want, be it forest, be it water, be it agricultural land, or it could be even the snow cover in the mountains. So fundamentally, you have the platforms which are put into place, either drones or aircrafts or spaceborne. But what data do they collect? The satellites. Basically, we all know that we have the solar energy coming from the sun, and then it passes through the atmosphere, it interacts with the Earth's surface, and then part of that energy gets reflected, and part of it gets scattered in the atmosphere. And whatever energy that is getting back into the sensor, based on that, you try to create images. That's what is shown here below as natural color and false color. A natural color is what we actually see as a human being. For example, vegetation, I see as green. So here also, the natural color composite, probably you'll be seeing the vegetation in green. Whereas in false color composite, what you are seeing as vegetation is actually in red color. So I can use different band combinations in the satellites and assign different colors to it to create these color composites. And if you look at the energy that is coming from the sun, and we call them as electromagnetic radiation. So it is the EMR spectrum, and it has a wide range of wavelengths, starting from the ultraviolet rays to your gamma waves. But as a human being, we don't see all these wavelengths, and what we see, as indicated here, the visible light, which is basically 400 to 700 nanometers. And in that we have 400 to 500 blue, 500 to 600 green, and 600 to 700 red. And this is the area, or this is the bandwidth only with which we are able to see the objects as such in our natural earth. And the combination of these three primary colors makes us to perceive objects in the true colors. For example, vegetation reflecting more of green, you are able to see vegetation as green and so on. But the main advantage of satellites is that I don't need to restrict my understanding of the objects only with respect to visible light. I can have sensors, charge coupled devices, which can sense the energy that is returning from the earth in other wavelengths too. For example, when the sun's energy is coming in all these wavelengths, from all these wavelengths, some part of it is going back to the satellite. So I try to see the wavelength, the energy reflected from that portion of the wavelength other than light. For example, it could be in the infrared, it could be in the microwave, and so on. And when we talk about satellites, as I said, we get repeated data. That is because, as shown on the right-hand side, once a satellite is launched, it can be put into basically two types of orbits. One is known as the polar orbit, where the satellite moves from one pole to the other pole, say north to south, and it keeps on doing that till its design period. As I said, it could be 4 years or 5 years, whatever it is. But for the satellite to see the same area on the Earth again, we call that as a revisit period. So that is probably, it could be, if it is a one satellite, it could be 16 days, meaning that every 16th day, I'll be able to see the same portion of the Earth from the same satellite. So I'll be able to get satellite data every, say, once in 15 days. And there are constellation of satellites. I can send similar satellites, maybe 1 in number or 3 in numbers or 5 in numbers. Then I call them as constellation of satellites. Then using these constellations, I'll be able to get see the same portion of the Earth, even probably once in 2 days or once in a day even. The other possibility is to have what we call as geosynchronous orbit, which will be not traveling from pole to pole, but it will be parallel to our equator, but at a height of 36,000 kilometers. So there, for example, our weather satellites and communication satellites, they will not be in polar orbits, but they'll be in the geosynchronous orbits, wherein you'll be able to get the satellite data once in 30 minutes even. That would be quite useful for weather forecasting and things like that. So we have meteorological communication satellites coming under this category, but all Earth resources applications, most of them, they belong to polar orbits. And when I said that from the satellite, we'll be able to see like water, forest, agricultural land, etc. How do satellites distinguish between these two? As a human being, we all say that we have our biometrics, which are unique. We have our signatures, which are unique. Based on that only we are identified who we are. Similarly, every feature on that surface has a signature. We call them as spectral signature. That's what is shown in the graph here. So on the x-axis, you have the wavelengths, and in the y-axis, like the kind of reflectance that particular object is going to emit or reflect. For example, in different wavelengths, different objects reflect different amounts of energy. So using this, it's quite possible to differentiate different types of objects. For example, even if you take water, a very clear water will have a very low reflectance, and whereas a water with high turbidity will have a higher reflectance. So this helps me to identify whether the water is clear or water is turbid and so on. And as I said, like we have different bands in the satellite. each band will have a particular wavelength motion. For example, if I say band 1, it could be say 0.4 to 0.5. Band 2 could be 0.5 to 0.6 micrometers or 500 to 600 nanometers and so on. So I'll have different bands in the satellite, and it could be 12 bands or 20 bands. It depends on what satellite it is and how many sensors they have them in the payloads. So when I try to plot the pixel value, what energy that has been received by the satellite in that spectral region in a pixel. Pixel is nothing but the minimum area from which the energy is recorded by the satellite when it is receiving the energy from the Earth. So it could be today we have capability with the pixel size up to 30 centimeters. And we also have satellite data which has 1 kilometer pixel size. For example, all your weather satellites, what we see as INSAT 1A, 1B, etc., they all have pixel size as 1 kilometer roughly, because weather doesn't vary every 30 centimeters. But whereas there are other applications where the pixel size has to be small, so that you are able to differentiate different objects on the Earth surface, which you need to differentiate for various application domains. So when I try to plot the pixel values in each of these bands, like for example, in this case, band 4, band 5, and band 6, so it forms specific clusters. Each of these clusters basically belongs to one particular category. For example, spectral class 1 could be vegetation, spectral class 2 could be water, and so on. So there could be several spectral classes, and I try to train the satellite images using different software, which will help me to identify different classes, and I can have supervised classification as well as unsupervised classification of satellite images. And before we actually proceed further, for example, what you're seeing here is that the nature sends the electromagnetic radiation towards the Earth's surface, and what you're seeing as a graph with a gray color is the solar radiation that is at the top of the atmosphere, and what you see as in the white color within that gray color band is what you receive as solar radiation at sea level. So you can clearly distinguish the difference between these two graphs. Basically tells you that the energy when it is traveling through the atmosphere. For example, when I look at a tree, probably I'm looking at it from few meters away. So the distance between me and the tree will have probably a length of few meters. Through that only I'm seeing it through the atmosphere. Whereas when I launch a satellite, the satellite is at an orbital height of say 600 kilometers. So between the Earth's surface and the satellite, there is 600 kilometer length of atmosphere through which the energy has to pass. So when it passes through that 600 kilometers, then some of the energy gets scattered, some gets absorbed, some get emitted, and so on. All this reduces the amount of energy that actually reaches the Earth's surface. And similarly, when it is getting reflected back, again, atmosphere plays a role. For example, we all know that the atmosphere has different constituents like N2O, O2, O3, CO2, and water molecules. So all these have a lot of absorption characteristics, and they absorb certain amount of energy. And despite all this scattering, absorption, etc., we are able to receive sufficient energy so that you are able to place a satellite, and the satellite is able to have enough observable signals which can be processed later to analyze different objects. And this is to talk about pixels. For example, like what you're seeing here is 30-meter satellite data, and this is 20 meters, and this is 10 meter, and this is our IRS-1C, 5.4 meters, Indian remote sensing satellite. And here what you see on the bottommost left is 30 centimeter satellites. As you can see, all display airports, but in the 30 meters, probably you are able to see the runway and associated infrastructure, buildings, etc. But whereas in the 30 centimeter, you'll be able to see even the paint markings on the tarmac and in the runway. So it all depends on like what resolution that I need for a particular application. As I said, all your weather application does not need 30 centimeter. probably you can go to very coarse resolution. And for other application, depends on whether it is in agriculture or in urban planning and so on, people try to use different resolutions. So resolution is actually, as I said, it's a pixel size. So if you're talking about the area of interest also, for example, my area of interest is going to be entire globe, let us say, for climate change studies, then probably my study area is going to be entire globe. Then probably I cannot use a 30 centimeter data to analyze such a large area. So naturally, I'll go in for a coarser resolution. And whereas if it is continental level, it could be still further lesser, and national level still lesser, and so on. And whereas at local level, maybe for Chennai Corporation, you would like to know how many buildings are there, what is the rooftop area, etc. Then if that is my application, then for tax collection purposes, then probably I'll go in for 30 centimeter. And this is the kind of situation that we have. And this list is not complete. I just compiled like what are available in some of the literature, but the number of satellites that are actually revolving currently is in the range of say 6,000 in numbers. And each one of them have different purpose for which they have been sent there. Some are spy satellites, military satellites, and some are for Earth resources mapping, and some for atmospheric studies, and some other for ocean related studies and so on. And this list gives you different satellite sensors, and whatever is free, that also has been indicated. And for example, most of the high resolution satellite that you see here, for example, where the spatial resolution is say 80 centimeter, 60 centimeter, 30 centimeter, etc. You don't get them free of cost. And they're all commercial satellites, not launched by governments, but private companies. And they do give you satellite images, but at a cost. For example, if you want to acquire a fresh satellite image of 30 centimeter resolution, probably it could cost you around roughly say $22 per square kilometer. And as you could see on this table, like how much area is covered in each orbit is the orbital swath, and the height of the orbit is given. I said it can vary from say 500 to 900 kilometers. That is height at which the satellite is going to revolve. And then spatial resolution is given, the pixel size, and temporal resolution. Once in how many days you will be able to get the data of a particular location. That's what is temporal resolution, and how many bands they have, and the spectral range, from which range to which range they are observing the energy, and so on. And this is the difference basically. For example, what you see on the left hand side is what we see as a human being. But if I use an infrared camera or infrared sensor, the same vegetation would look like this. And probably here on the left hand side, you can see that there is a river going on here in this image, which is light blue in color. But whereas the same river appears as purely black in color in infrared, because water absorbs most of the energy in the infrared band. So that is the reason why it appears black. So satellites in different bands see different objects on Earth's surface in different colors. And we also have what is known as spectral resolution. So the amount of energy that goes into the satellite can be split into a minimum and maximum value. For example, 0 to 255, we call that as a 8-bit spectral resolution. So when nothing is reflected from the Earth, it will get 0. When the entire energy gets reflected, it gets 255. This is 8-bit, and we also have sensors which have 11-bit spectral resolution and so on. So each pixel will have a particular value. So minimum three bands are required to be combined to produce a color composite. That is what we call as satellite images. And remote sensing basically helps you to prepare maps. So this just to give you an idea like how satellite data can help you to get historical references. For example, this is with regard to Chennai city. This is a map of Chennai city prepared by our Britishers way back in 1909. And you could see that there is a very big tank here called as long tank. And if you superimpose that onto the current satellite image, it's probably most of them belongs to your T Nagar and Panagal Park area, which is a commercial hub today. And you can see this particular Adyar River here, and these were Adyar estuary area. And so satellite data and maps, historical maps, gives you a lot of references with regard to in the past what we had. And today, apart from the list I have shown, there is a satellite by name Corona. And of course, the name is not very attractive nowadays, but still the satellite is basically named Corona. It was originally a spy satellite by US. And recently, in the last 2-3 years, it has been declassified. And these declassified images are also available in open source domain. So that means these data were collected in the year 1960s and 70s. So it helps us to know like how our cities were probably 50 or 55 years back. And this is another slide to show that during disaster management. So this is 2004 tsunami data. So before the tsunami struck, for example, Bandayes is the location here. And this is the plate movement that has occurred in this location. So this is the area where the plates have collided and moved. And this created, we all know that the tsunami, the red bands that we show on the coastlines here, those are the areas that were badly affected by tsunami. And you could see Bandayes was very close. And this was the situation before the tsunami. And right after the tsunami, this was the situation. And now, with this brief introduction to remote sensing, like how the data is collected, now let us go like what data products can be generated from space. As I said, the main advantage from space is that I can monitor a lake probably in our neighboring countries like Pakistan and China, as well as in USA. I don't need anyone's permission as long as I have the satellite data. So that means global mapping is possible. Similarly, they also could do what we have. So that way, satellite data provides you global monitoring, irrespective of national boundaries. As long as you have some in situ data available from those locations, you should be able to do the monitoring of your water body in any country. And coming to what are the different products that you can generate. For example, I can find out the height of the sea surface, and then I can find out the temperature of the sea surface. And with regard to surface and groundwater, I can calculate evapotranspiration. I can calculate groundwater anomalies and snow cover. And in addition, I can also do like surface water assessment. For example, surface water area of lakes, rivers, etc. periodically. And then the groundwater anomalies, as I said. And in addition, maybe you are more interested in this, the water quality assessment. And once again, it can be done at global, regional, local level. And the main advantage being, you should be able to temporarily monitor any water body for its quality. For example, like how do you measure sea surface height? So you have a satellite which has a radar altimeter. Altimeters are basically which measures the height by sending a microwave pulse. The pulse starts from the satellite, gets sent towards, for example, the pulse is sent from here vertically down towards the nadir, and then it hits the sea surface and goes back. We know the velocity of light, so the time it has taken, the starting time of the pulse and the receiving time of the pulse with velocity of light, you should be able to get what is this value. We call it as range. And at what height the satellite is there using GPS, we know. So the difference between satellite height and the range basically gives you the height of the sea surface with respect to an ellipsoid. So with this, the sea surface height is determined with an accuracy range in terms of few centimeters. So that means globally, remember On the land, getting to know the elevation, probably you have different techniques. And looking at the sea, probably you know 2/3 of your globe is your water body, and trying to know what is the sea surface height by conventional surveying methods, that is never going to be feasible, and it's going to be quite time consuming. So probably remote sensing is the only technique which can provide you the global visualization of what is the sea surface height. For example, what you see on the left-hand side is normally what we perceive as Earth, a good round shaped sphere. But in reality, Earth is not like that. Like what you see at the bottom on the left-hand side is actually how Earth looks like. Because at the top, it cannot look like this because we also have Mountain Everest and several deep valleys. So it cannot be a perfect smooth sphere. But if you look at even the sea surface is not at the same level. Normally, as a common man, we all see that when you go to a sea, the sea is perfectly level. It's not so. For example, if you look at this global map, so the range is from say minus 80 to plus 80. So meaning that there is a height variation of 160 meters. If you look at the entire sea, and if you look at India, Bay of Bengal and Arabian Sea is not at the same level. So that is why we use the term mean sea level for all our engineering applications. So sea level is a dynamic phenomena. It changes, and it changes from one place to the other. Like you have mountains and valleys on land, you also have bulges of water body. You don't call them as mountains. The sea water also has similar to mountains, a bulge, or it can be a depression in the sea itself. And this is with regard to, as I said, the satellite data helps you to globally monitor different things. For example, whether it is chlorophyll concentration in the sea or the sea surface temperature in the oceans. All those things can be monitored, and you can have a time-lapse simulation like this for several periods of years. And these kind of data are globally made available free of charge by different agencies. And these could be used probably with kind of limitations they have. And once you feel that these data are going to satisfy your research requirements with regard to the accuracy levels, then probably these are ready-madely available for quite a long period, and people can make use of this for their own applications. So now, if you look at, we'll just get to know each one of these applications. As I said, the surface water area of a lake, how do I measure? Because it varies. For example, if you take the water, drinking water supply reservoirs for Chennai, say be it Pundi Reservoir or Cholavaram Reservoir or water Red Hills, and so on, Viranam Lake. So all these reservoirs have different water spread area at different months of the year. So satellite data can have ready-made tools. So I don't do any manual intervention. I just feed in my satellite data. It just tells me which are the pixels which are water related, which are the pixels which are not water related. So all water related pixels gives me the area of water spread. So how much water spread area is in a lake or in a reservoir can be automatically mapped using ready-made algorithms. And you don't need to do any manual work on this. And a lot of algorithms are available in the open domain where we can readily extract water bodies. For example, in our country, National Remote Sensing Center is there. And at national level, they extract water bodies once in 15 days. So every 15th day, how much of water spread is there on the surface is known through satellite data. And water body fraction also is known. For example, our entire country is divided into a 3-minute by 3-minute grid. In each grid, how much of water spread is there? So that data is also made available by NRSC through the Bhuvan web portal. And similarly, at the global level also, some of the studies have been done of major water bodies. Probably when I use the term, like we should not be carried away to uh, think that, for example, very small water bodies like temple ponds or lakes, which are of very small size, probably it will be covered by 1 or 2 pixels in the satellite resolution, may not be suitable for monitoring. So depending on the resolution of the satellite that you use, when you have sufficient number of pixels covering the water body, then probably you can as well monitor them over a periodical term. And not only surface area, but you can also get water surface elevation. So not only sea surface height, I can get water surface height in the lakes and in the rivers by using TOPEX, Poseidon, JSON2 satellites, and so on. So you get water surface area as well as water surface height from the surface water. And for example, like there were some critical studies that were conducted by NASA. For example, most of us, we know the Lake Chad, so which borders, I think, 3 countries in Africa. And this was one of the largest freshwater lakes in Africa. And you can see like the water spread it had in 1973 and how much it has reduced in 76 and in 79. And today it is in a much pathetic situation. And as you could see that on the right-hand side graph, there were a lot of drought situation in Africa, and that has resulted in say hydrological droughts, hydrometeorological droughts with less amount of rainfall, and this has reduced in less water spread area. And in fact, Lake Chad is responsible for several millions of people being dependent on it for drinking and irrigation purposes. And as you could see that the Lake Chad water level has periodically declined over a period of years. And this kind of monitoring also has been done with regard to several critical habitats. And this is another example, like, for example, if you have a reservoir, and all of you know that the reservoir gets water from a river, the river has a catchment area. In the catchment area, when there is a rainfall, the water that is coming through the river, you try to block it with your dam, and then a reservoir is created. For example, this particular reservoir, in various months, in different dates, the satellite data is given, and the water spread area is shown on the right-hand side. So I can ready-madely extract how much water spread area is there in this reservoir on different dates. And on those dates, I also know the elevation in the reservoir from the reservoir maintenance authorities. They'll tell you on this particular date, this was the height. So I also know the height. I also know the water spread. Then I plot a graph like this between water spread and elevation. And you could see 2 lines here. And one is the original data when the reservoir was operational. And the second one is what you see today. So the difference clearly tells you how much of sedimentation has occurred, how much of silt has been accumulated under the water spread area. So this results in less storage capacity of the reservoir. And once this keeps on increasing, then probably at one point of time, the reservoir becomes non-operational because it can no longer store functionable or utilizable amount of water because of siltation. So if you want to monitor siltation, then probably satellite data is going to help you, like how much silt is getting or how much sediment is getting carried away through the rivers. And since you are creating an obstruction across the river, all of these sediments gets deposited in the reservoir, and probably desilting is to be done. This is at operational maintenance level. On the other hand, you can go to the catchment area and try to take conservative measures which reduces erosion. So if you take conservative measures in the Watchman catchment area, watershed catchment area, then that's going to send less soil through the rivers, and probably you are increasing the operational lifetime of the reservoir. So for all these scientific inputs, satellite data can play a role. And then sea surface temperature, again, there is another valid input which you can derive from satellite data. So you can measure sea surface temperature. For example, like when we talk about electromagnetic radiation, we said there is visible light, there is infrared light, and in this infrared region, there is a band called thermal infrared, normally in the range of say 9 to 11 or 12 nanometers. So these bandwidth range is actually very sensitive to the temperature changes. So the amount of energy that is received in this bandwidth is actually emitted back by the Earth. This energy can be measured, and from which, based on the emissivity of the material on the Earth's surface, you will be able to extract what is the temperature of the object. So that means each pixel at what temperature it is. So not only we get sea surface temperature, we also get land surface temperature. And there are a few web portals wherein whatever data product I talked about, like sea surface temperature, and then sea surface height, chlorophyll, temperature, salinity, wind. For example, this screenshot just tells you the ocean currents, geostrophic ocean currents, how the ocean currents are moving currently or on a particular date. So this portal gives you information on all the parameters that are shown on the left-hand side. And it's not only about current data, it also has past data. So you can just have a look at it and then get to know like how temporally these data are varying. And these data are quite useful to understand like the energy balance studies that we normally do. For example, like when I say the electromagnetic radiation is transmitted back towards the satellite, we need to have a radiative transfer model, or your hydrological cycle, for example, requires energy balance studies, like how much water is evaporating and how much rainfall you are getting. All these are, we call them as energy balance models or energy transfer models, and different models are available, and using them, one can use this data as inputs into those models. Now, it's not only about surface water, we also get some information about groundwater. For example, satellite data is not capable of the EMR energy that we are getting is not capable of penetrating into the ground and giving us some information, but people use different other analogies, like whether without penetration, can I use other kind of information to know what is happening below the ground. For example, what you see on the left-hand side just gives you like how important is groundwater. That is 50% of drinking water at global level is from groundwater source, and 70% of the groundwater withdrawal is used for agriculture, and 38% of the land globally is being benefited by groundwater irrigation. And on the right-hand side, if you look at the global scenario, you can see that 30% of all our fresh water is basically groundwater, and almost 68%, 68.7 they say, it's all stored in the glaciers and the snow ice caps. And what we are talking about as rivers and lakes, reservoirs, etc., is basically 1.2% only. So the groundwater is 30 times more compared to surface water, and it's all the more important to know what is happening with our groundwater. And the table on the bottom right-hand side just tells you how scary is our scenario. For example, if you look at groundwater extraction for irrigation, India is one of the leading countries with 89%. And of course, if you take, say, 1,000 liters from the ground, and if you're able to replenish it back with a groundwater recharge with 1,000 liters, that is not an issue because the supply demand gets matched. But nevertheless, what happens is if I extract 1,000 liters and I use it for different purpose, domestic irrigation and then industrial purpose, etc., but the waste is let out into the river and finally it goes to the sea. So out of 1,000 liters, if I'm using 100 liters and remaining 900 liters, I'm sending it to sea, which again increases the volume of the seawater. So groundwater extraction, unless it is replenished 100%, it creates other kind of issues to us. So for this purpose, for example, to know more about groundwater anomaly, so they have launched 2 satellites. For example, the satellite is named GRACE. And when GRACE is launched, it is always launched as 2 satellites in tandem at a specific distance between them. That is, each satellite, satellite A and satellite B, both are same satellites, GRACE 1 and GRACE 2, but the exact distance between them will be 220 kilometers. They are placed in the orbit in such a way that the distance between them is 220 kilometers. And by continuously measuring the distance between these 2 satellites, scientists were able to decipher, like, can it be related to the gravity anomaly? And the gravity anomaly, once again, is related to change in mass distribution. And that mass distribution, it can be again correlated to changes in groundwater. So that is how groundwater anomalies have been mapped. For example, when these 2 satellites are flying in orbit, they also fly over the sea. And as I've already told you, the distance between the satellite will not vary much when they are flying over the sea, because there is no huge mass change over the oceans. But when it passes over the land, there is a gravitational pull on the spacecraft. When the first spacecraft enters, there is a gravitational pull on it, and this increases the distance between the satellites. And this is exactly measured using the microwave ranging instrument that you have on board. So the microwave ranging, like in radar altimetry, so it sends a microwave pulse and exactly measures what is the distance between the satellites. So which will show a minor changes when it's passing over the landmass. Similarly, when the second satellite is also entering, there will be a change. And these changes between the distance between the satellite is exactly measured. And these are related to the groundwater anomalies. And you also have an accelerometer on board, which will measure the changes in the distance between the satellites due to non-gravitational forces like atmospheric drag, etc. And these error sources will be eliminated so that you try to narrow in on the change in distance only due to gravity change. And as you could see here, like what GRACE satellite measures is basically, as I said, the changes in gravity anomaly are related to the water storage anomaly. So they use the term terrestrial water storage, TWS. So the terrestrial water storage actually consists of all changes, not only in groundwater, but changes in the snow. For example, there could be snow melt from the polar regions, and there is some soil moisture that is available in the Earth's surface, and there is groundwater. So all these 3 components are there. So you try to calculate the total impact of all this on the gravity and try to term this as terrestrial water storage. And using satellite data, you cannot distinguish how much is actually because of groundwater, and for that you need to use other parameters as well. But as such, if you want to map how much change has happened in the terrestrial water storage, consisting of groundwater, snow water, and then soil moisture, all these included, then that is what this figure shows, like terrestrial water anomaly. But if you want to know from terrestrial water storage to groundwater anomalies, then probably I need to separate out these components. For example, change in groundwater storage, that is what I'm interested in. And then change in soil moisture, and then change in snow water, and then change in surface water. So all these parameters, fortunately, they are all observable and measurable using satellite data. So we have different models. For example, one such model is Global Land Data Assimilation System, GLDAS. So these models gives you the value of these variables, which can be substituted in this equation, so that what you have on the left-hand side, like change in groundwater storage, delta GW they call it, can be measured. And this anomaly gives you some idea like what is happening below the ground. For example, this is the change in groundwater storage anomaly mapped globally across the globe, and you can see that it's in millimeters, and in some areas it's quite high, and in some areas it's quite less. So this kind of analysis with regard to groundwater quantitative assessment, it's not going to exactly tell you like how much volume is there, but it's going to tell you how much change has occurred. For example, from the month of say, so when we take our academic, I mean our meteorological calendar, say our peak summer, let us say, is from January to June. Then during this period, the extraction is going to be more, probably precipitation is going to be less. I'm talking about the East Coast. Then probably from the months of say October to December, you have very good rainfall through your monsoon, and recharge is going to be there. So all this happens throughout the year. So one hand you have no rainfall, and in monsoon season you have heavy rainfall, recharge takes place. So there is continuously changing groundwater heights, and these groundwater heights gives you the change in groundwater storage. So that you are trying to monitor using satellite. And in fact, GRACE satellite has been used in one of the studies in California drought, and they were able to successfully quantify like how much of anomaly is there in the California region in USA. And now coming to probably a more interesting topic to ICCW, like can I also have some kind of measurable parameters from satellite with regard to its quality? For example, like all man-made and natural impacts create pollutants in your fresh water sources. For example, like man-made, because we have plenty of examples, we all know that the anthropogenic impact of pollutants into the freshwater sources. And what you see on the right-hand side, you can see that this from a particular lake, wherein you all know that water quality can be measured using what is known as a Secchi disc. It's a circular disc painted in white and black in different quarts, and then it is suspended by a rope, and it's sent into the water. And up to what depth you are able to see the disc clearly, you call that as Secchi depth. The Secchi depth is actually directly related to how clear the water is. So the more the Secchi depth, the more clearer the water is, or less turbid the water is. For example, in this lake, if you look at the Secchi depth, probably in the year 1965, it is in the range of say 31 or 32 meters. And by 2020, it has come down to say 22 meters. So there is a loss of about say 10-meter clarity in terms of Secchi depth in this water. So turbidity is one. Of course, this method requires manual visits to the field, and then you need to immerse the Secchi disc and try to assess what happens to the clarity of water in terms of total suspended sediments, we call it TSS. But these total suspended sediments can be measured using satellite data. This is again lake shed. The water quality again, for example, suspended particulate matter has been assessed using satellite data. So this is the UNESCO water quality portal, where regarding the lake shed, a lot of temporal data is available. Probably you can just have a look at it. And this is chlorophyll A concentration in lake shed, like the date on which the chlorophyll concentration is measured, and its quantity, you can probably have it visualized on different dates. And similarly, as you could see in any freshwater lake, the chlorophyll and the sediment concentration is going to vary. This one particular lake, where from January to October on different dates, you can see different chlorophyll contents. And the interest would be, can I map this from the satellite? The answer is yes, you can do it. For example, for the CHUD water quality portal. So these are the periods in which the data is available. So you get all this parameter data. For example, turbidity, suspended particulate matter, dissolved organic matter, chlorophyll A, and then cyanobacteria, surface water temperature, and then water surface area, and then water level. So these are the parameters that are available for visualization from the year 2015 and water level from 1993.
We should be sensitive to time.
Yeah. How much time do you have more?
We are at 4 o'clock now.
Can I take another 5-10 minutes?
Yeah. We should also allow some questions. Yeah. Thank you.
Yeah. I'll try to finish it in 5-10 minutes. Yeah, this is regarding water quality. As I said, why remote sensing? It allows you anywhere, anytime, any size, except for smaller size ponds and water bodies. But irrespective of the location, irrespective of the time period, you should be able to get the quality data. And there are many parameters that are assessed, but these are the data that we are going to discuss now, like CDOM, chlorophyll A, total suspended solids, and of course, temperature and salinity we have already seen. And these are the open source data. So the main advantage again here is that you don't need to pay anything to use these satellite data. Landsat is from USA, and Terra Aqua is from Moody's, again USA, and then Sentinel data is from Europe, and SNPP and JPSS, again, these are joint planetary satellites, polar satellites, which are launched for Earth observation. But all these satellites are available free of cost, so you can download it for any part of the globe, and these are the different bands available with their wavelength regions in different satellites. And with regard to water quality assessment, what actually is processed is the amount of energy that is reflected from the water surface towards the satellite. We all know that at every pixel we'll have a value, and what we call this as is that top of atmosphere reflectance or radiance. So that is a value that you get. But the amount of energy that is reaching the satellite is not only from the water, but it also contains components from atmosphere. Atmosphere also scatters, atmosphere also reflects, and there are other components. So I need to deduct all these components to exactly find out what is how amount of energy is actually leaving the water surface. We call this as water leaving radiance. So from top of atmosphere radiance or reflectance, I need to get water leaving reflectance or radiance by doing the atmospheric correction. And to do this atmospheric correction, we all know that like how each object, as I said, through spectral signature, like how the water molecules in the atmosphere react, how much they absorb, how much they reflect, etc. And different models, radiative transfer models are available. For example, this is the spectral signature, which tells you like how different components in the water itself, with regard to remote sensing reflectance, with respect to wavelength, how do they vary? So I use all this information to know which band should I use to map sediments, which band should I use to use chlorophyll, and which band should I use to map CDOM, etc. And this is the overall methodology. For example, like we all know that satellites go around the orbit. So for example, if you want to measure water quality in Pulicat Lake, I exactly know on what date the satellite passes over Pulicat Lake. All polar orbiting satellites passes the equator near to about 10 to 10:30 a.m. So that is how the orbit is designed. So I should be able to present on that date on which I want to assess the water quality in the Pulicat Lake with a boat, with my spectroradiometer and water bottles to collect samples. So at the time of satellite pass on that date, I also collect in situ water quality data. So this in situ water quality data consists of two parts. One is water samples, which can be analyzed in the laboratory for different parameters. And I also have a spectroradiometer, which will tell me the spectral signature of the water body in different bands. So water leaving radiance is basically measured from this, and top of atmosphere radiance is measured by satellite. By knowing these two, I apply the atmospheric correction, and based on that, I come at how much of actual energy is leaving the water surface. So that helps you to correlate that energy with the in situ water samples that you have. So that means I can map chlorophyll, I can map nitrates for eutrophication of lakes, and so on. So for different application, I try to map different pollutants. So what is basically done is, in this atmospheric correction, you will have the darkest pixel in the satellite data. So the number that is associated with that pixel basically is contributed only by the atmosphere. So that is another information that I get from the satellite regarding how much is the atmospheric component. So using all this information, I develop algorithms which helps me to prepare the pollutant concentration in different water bodies. For example, left and right shows you the corrected satellite data on the right hand side for atmospheric correction, and with atmospheric gaze, what you see top of atmosphere in the left hand side. And this is one case study for 2 reservoirs in China. And what you see on the left hand side is the different satellite data that they've used on different dates. And this is the water quality data that they have from the field. And finally, you try to establish linear regression models like this, where the turbidity level is on the left hand side, and your B2, B3, B4, B5 are nothing but satellite bands, B2, B3, B4, and B5. And the coefficients associated with it are basically established using linear regression models. So similar to turbidity, I can have different regression models established for chlorophyll, for CDAM, and so on, for different parameters. And as you could see, like these are the acceptance levels of the results. So they have 55 samples. Whatever you are seeing in the blue color, they were all used for model calibration. So the turbidity that is actually used for model development, and what you see on the red hand side, they are used for model validation. So the model validated results, they're quite matching with the actual data that are measured. So this way, you'll be able to develop empirical models. But the drawback of this empirical model is I cannot use this empirical model for another lake, for another water body. So it is location dependent. For whatever water body you are developing it, you need to use it for that water body with frequent atmospheric corrections. And similarly, several people have established several empirical models with the different band combinations. And these are for chlorophyll estimation. And finally, by using this empirical model, this is another study area and the Suez Canal, where you can see that the concentration of the pollutants could be mapped over different time periods. And then, of course, probably if the question is like, do you have to do all this manually? Not essentially. Once you have some basic knowledge, there are a lot of toolboxes available which are open source. So you just download the satellite image, feed it into the toolbox, and then provide sufficient data that is required for the analysis. And then you end up getting the deliverables. And again, this is open source. And as I said, you can get the chlorophyll concentration or any other pollutant concentration. What you see on the left-hand side is at the local level. What you see on the right-hand side is at global level. This is quite possible to map using satellite data. And of course, commercial solutions are also available. For example, like DHI, you might have heard about. They do a lot of water-related software marketing. And DHA also has come out with what is known as DHA Grass. So if you buy DHA software, this is a commercial solution where you can download satellite images and you can ready-made calculate the water quality. And empirical mode again is not the only way that you do water quality analysis. There are analytical modes which use radioactive radiative transfer models and biooptical models, which can be used for the propagation of light, both within the water as well as in the atmosphere. And you also have semi-empirical modes. And finally, machine learning and artificial intelligence modes are also available. And of course, it's difficult to cover everything in 1 hour, but a lot of information is available, and the technology is evolving day by day. And some Indian examples are also given in these case studies. And then most of the information is taken from NASA RSET website. They call it as NASA Applied Remote Sensing Training Program, and many of you can attend. And thank you for your patience listening. So now I am open for any discussion.
Well, I would say beautiful presentation. You covered the depth and breadth of this whole subject. Obviously, one can go for an entire course lasting a semester on such a subject. So thank you very much.
Thank you.
We should get some questions. But before I invite questions, let me pose this sort of rather bewildering question to me, that we have so much of quality data. We have this data available across. We have high resolution. We have satellites such as GRACE. We have quality, quantity, all of these can be mapped. Now tell me, why is that then there are water disputes?
Water dispute is basically because, for example, when I was a research scholar way back in '96, doing my PhD, when I was doing my literature survey, one of the literature was saying that if there is going to be a third world war, it will be due to water.
Right.
And most of the surface water that we get, for example, out of 365 days, if you look at Chennai.
Let me be specific. I mean, in the context of, let us say, Tamil Nadu and Karnataka, or between India and Pakistan, or between Punjab and Rajasthan. So all of these are groundwater disputes or water flow, surface water flow issues. Probably I should have been a little more specific in my question. Yeah, thank you.
In all these cases, for example, when Tamil Nadu says the amount of water that is received is so much, it is disputed by Karnataka. We all know that we have sophisticated instruments which can measure quantitatively and qualitatively, how much water is being received. But both ends, they don't believe others' data. So probably I attribute that as the main reason rather than actual dispute being existing.
Or is there a different way of interpreting the same data?
For example, I can give one small example with regard to Mullai Periyar Dam. For example, there were a lot of dispute regarding raising the water storage height. So in fact, our institute was tasked with what will happen if I raise the water level to 142 feet. For example, then we collected satellite data with regard to water spread at different heights. Then without telling the Kerala government, from Tamil Nadu side, we traveled by boat, collected the ground related information, came back and then simulated if the water level is raised up to 142 feet, how much area would be flooded in Kerala. So when there are intergovernmental disputes, the data that is being provided by different governments, that becomes disputable, but probably a neutral body, if it exists and if it can assess quantitative and quality wise, then probably all these disputes could be avoided. And another reason is only 5% of rainwater is being used. Remaining 95% goes to the sea.
Sure. Thank you. Let's open it up for others. Pooja, please carry on.
There's a question by Romiel Samuel. Can we do bathymetric surveys via satellites, if I'm spelling it right?
Yeah, when it comes to measuring depth of water, we use, of course, sounders, echo sounders with boats you can use, that is ground-based. When it comes to airborne, we have what is known as a technology called airborne laser scanning. So where we have airborne bathymetric laser scanner, which uses two lasers. one in the green band and another in the near infrared band. One gets reflected from the water surface, other gets reflected from the lake bed or river bed. By knowing the time difference, we should be able to get the depth of water. But again, how much penetration can be had in a particular water body depends on clarity of the water in that water body. So again, second depth plays a role. So depending on the second depth, how much depth, for example, if the second depth is 1, then 3 meters can be measured. If second depth is 10, then 30 meter depth can be measured. So theoretically, up to 50 meters, laser scanning can help you to map the bathymetry. So that means near the coast, up to 50-meter water depth, if the water is clear, it's possible. And if the water is turbid, less than 50 meters, again is possible. But measuring ocean depth from satellite or airborne platform is not possible.
There's one more question by Mr. N.S. Murthy. Is there any foolproof method to recharge aquifers than normal percolation?
No, like it could be site specific. For example, like today, we are evolving technologies wherein carbon dioxide can be stored under deep aquifers. And similarly, people are trying to inject water into deeper aquifers for use later, but I don't know how prohibitively costly these technologies are. So did I answer that question or not?
Mr. N.S. Murthy?
Okay, thank you. Thank you very much.
Will there be any more questions?
Can I ask
Pooja,
a question?
sorry, yeah, go ahead, Mr.
I'm
Krishna.
Krishnasamy. Yeah. So Dr. Thirumalaivasan,
Yes.
I represent an NGO in Coimbatore called Sirutuli, and we're working on a lot of water management issues. And now our basic thing is the Coimbatore city gets water from Sirvani, major source of water.
Okay.
This lies within Kerala. The same interstate problem is there. And huge siltation is there across the dam. Catchment area or the water spread area has shrunk, the depth has come down, and it is only operating at about 30% capacity now. And as usual, Kerala, they are not increasing the dam. The dam is under their control. So they don't increase the water level up to the surplus and all those things. And the Coimbatore is being deprived of its share of water over there. Can IRS give us, from Anna University, can you give us the amount of siltation that has occurred over the years, say for the last 20 years, 30 years, how much this water holding capacity has shrunk? Can you please give us that from that? Can I approach you for that?
Yeah, you can approach us and it's quite possible. But only thing is, from the reservoir authorities, you should be able to get the baseline data. Originally when the reservoir was constructed, what was the storage capacity curve? They'll be having an elevation. What is the water?
Okay, that we should try to get it through our TWAD board itself. That is one thing.
Available, then we can compare it with current condition.
Okay.
Estimate like periodically how much siltation has occurred. That's
I will get in touch with you, sir. Thank you. Thank you. Thank you, sir.
Thank you.
There's a question by Mr. Paresh Rane. Can specific pollutant concentration can be found in a water body?
Yes, of course. It all depends on, first you need to know how that pollutant interacts with respect to the electromagnetic radiation. For example, as I said, different pollutants, we have different bands in the satellite. And I have not talked much about hyperspectral remote sensing. Hyperspectral remote sensing, probably they do not have 12 or 15 bands. They talk in terms of 200, 300 bands. And each of these hyperspectral data can help you to narrow down on few specific wavelength of electromagnetic spectrum, which is sensitive to a particular decrease or increase of a particular pollutant. And those specific spectral regions can be exploited to map a particular pollutant, be it nitrate or arsenic. First, we need to know how that pollutant interacts with the electromagnetic spectrum. So once that is done, then it's a question of identifying which bands can be used.
In continuation to the same question, Anik Panja has sent me a message saying that is it possible to monitor concentration of heavy metals, nitrates, E. coli, BOD, COD, etc. for drinking water using remote sensing of satellites for a small area of 2 meters by 2 meters?
Of course, the answer is an extension of what was there earlier, because what is measurable, what is not measurable, there is no clear distinction. So far, there are a lot of case studies available with regard to salinity, temperature, turbidity, suspended sediments, chlorophyll A, and then algal blooms, for example, presence of cyanobacteria or not. So like this, a lot of case studies are available. It doesn't mean that some other parameter is not measurable. Only thing is people would not have attempted it. So when I want to attempt to map a new parameter using satellite, then probably first I need to understand using a spectral radiometer how that pollutant reacts with EMR, then try to associate with the different satellite products which have similar bands. Then it's whatever you are doing, whatever procedure you are doing with regard to nitrates, the same procedure you are going to do with a new pollutant also, be it heavy metals or anything.
There's a question by Gurudev. Is any assemble AI model for deal with social economical issues? I am not sure if it is worded properly. Would you like to
Yeah.
unmute?
Hi, sir.
Yes.
Like you described, like AI mode is there,
Yes.
like semi-empirical models and AI models are there.
Yes.
I like to know about that. Is any AI model to connect with social plus water related issues directly? Is it available models are there? Is any available models are currently in development like this?
No, actually, like it's like indirectly referring it to social issues is not a difficult thing. For example, we gave an example of Lake Chad. So Lake Chad actually, as I said, it belongs to 3 countries in the border, and it was serving all the 3 countries as well. So now several millions of people are affected by the shrinkage of availability of fresh water in Lake Chad. So this is a social issue, like how much of employment has been lost and how much of agricultural area has been lost, the social impacts of the lack of rainfall in that area. So you can always link different parameters with this, but I am not sure of the existence of any ready-made model for this, but you can assess different parameters and link all these parameters to finally to a social impact or financial impact for them.
Okay. Okay. Thank you.
Pooja, I have a question. Dr. Thirumalaivasan, you had mentioned that 95% roughly of the rainwater is not being harvested, something to that effect. Is it possible to capture this information, let's say after the monsoons for any particular region, so that people immediately get some kind of a feedback as to what is available during the rains and how they could improve upon their harvesting potential?
No, the main problem is that, for example, as I said, the number of rainy days in a year, if you look at Tamil Nadu, it's hardly 40 to 50 days. And out of that 40 to 50 days also, heavy rains occur whenever there is a cyclonic activity in Bay of Bengal. Let us assume that it is 3 or 4 events, and each event contributing to heavy rainfall for 3 or 4 days. So effectively, heavy rainfall occurs for about, say, 15 to 25 days, let us say, in a year. So all the water that you get in the monsoon, which are supposed to be stored for 365 days, comes to us in a window of 15 to 20 days. So that means whatever water I am receiving in that 15 to 20 days, I should have enough area to store.
Store it.
In fact, if you go to internet, there are specific projects. One example I can give is Tokyo. if you go to this Tokyo project, where they have huge underwater tunnels, which divert water from the rivers into a huge underground reservoir, man-made reservoir constructed by concrete, and it's a very huge one. And they store all this rainwater under these underground reservoir, and later they treat it and use it when there is no rainfall. But the amount of initial investment needed to create such huge underground reservoir is one question. Capital investment is huge, but it's quite possible. You can. There are a lot of funding agencies like JICA and other Asian Development Bank. So if the government feels that diverting floodwater during heavy rainfall to underground reservoirs, because at surface level within the city, you will not find area to store. So the only way you can store water within a short few days is by having huge underground reservoirs. And Tokyo has already shown the world how it can be done. And probably it can be replicated in Chennai too to solve our water shortage issues.
Right. Now, apart from say metro cities, I'm wondering, and there are water stressed areas in the rural parts. There are many areas, even in Maharashtra, where during the monsoon there is a lot of water, but immediately there is a drought. So, in rural areas, do you think it can help in giving this so that?
See, again, storing water, either it requires construction of your dam, either bigger level or smaller level. And we all know, as Professor Pradeep has raised the issue of like why there is conflict. Like when Karnataka says they want to construct dam, we oppose because we are at the riparian end, at the downstream. So if the water originates within the state and it benefits only within the state, and if all the people living both in the upstream and the downstream agree, then probably all these solutions could exist. For example, if you construct a dam upstream, you can store water. That is true. But people in the downstream will be afraid that they are not getting their share. So you need to
no, if it is correct, if it is depriving somebody else, there'll be an issue. But if it is getting wasted and going to getting mixed with some kind of
sensitization has to be done. Like people need to be sensitized. Like you are storing excess water and you are not depriving them of what they are supposed to get.
Yeah, I was just inquiring if this kind of information can be taken from the satellite data and processed, and then we can present a case.
Data doesn't tell you like how much water is going to the sea, but
only the area.
We all know how much rainfall is there.
Right.
So from the rainfall, we can estimate how much water has actually reached that surface, and you need to account for how much of recharge would have happened.
Right.
It's like converting rainfall runoff equations.
Okay.
We have a lot of
Got it. Yeah. Thank you.
Thank you.
I believe we are headed towards the end of the session. I would just like to thank Dr. Thirumalaivasan. Thank you for the phenomenal presentation and giving us various insights into remote sensing. It was amazing to watch the 3D model of the shape of the Earth, which is different from what we see. And I believe we will get in touch with you shortly for more such collaborations. And thank you so much for sparing your valuable time in presenting a water talk for us. Let me all request all the participants to spare a few minutes.
So before that, let me also also thank Professor Pradeep and his team for giving me this opportunity. And though we are just across the road, both campuses, but still we have not interacted so far, and we are willing. So anytime, if you feel that this technology can be of some help, certainly we are ready and willing to collaborate. Thank you.
Thank you so much, sir. We will definitely get in touch with you. I would just like to bring all of your notice to what we do as an organization. We have we have a lot of hopes on implementing various kinds of projects with respect to achieving water security and safe, clean drinking water for everyone. And our aim is to continually enhance the water availability for all human beings, living beings, to work towards water security mapping, and also create some webinars and training programs and awareness campaigns for better understanding of water related aspects to people. If you are a water warrior and envision a water rich future, it's time to pitch in and do your bit. I've posted a Google form link in the chat box. Please go through it and connect with us to know more about the details. And also, thank you everyone for sparing your valuable time in joining us for this session of Water Talk. We will be hosting such Water Talks with various experts on every last Wednesday of the month. And next schedule is on 30th of August. So I would request you all to please join us again and let us make another event a successful one. Thank you so much.
Thank you. Thank you very much.